Black holes are powerful cosmic engines. They provide the energy behind quasars and other active galactic nuclei, AGNs. This is due to the interaction of matter with its powerful gravitational and magnetic fields. Technically, a black hole doesn't have a magnetic field on its own, but the dense plasma surrounding the black hole as an accretion disk does. As the plasma swirls around the black hole, the charged particles within it generate an electrical current and magnetic field. The direction of the plasma flow doesn't change spontaneously, so one would imagine the magnetic field is very stable. So imagine the surprise of astronomers when they saw evidence that a black hole's magnetic field had undergone a magnetic reversal. In basic terms, a magnetic field can be imaged as that of a simple magnet, with a north and south pole. A magnetic reversal is where the orientation of that imaginary pole flips and the orientation of the magnetic field flips. This effect is common among stars. Our Sun reverses its magnetic field every 11 years, which drives the 11-year cycle of sunspots astronomers have observed since the 1600s. Even the Earth undergoes magnetic reversals every few 100,000 years. But magnetic reversals weren't thought to be likely for supermassive black holes. In 2018, an automated sky survey found a sudden change in a galaxy 239 million light-years away. Known as 1S 1927 plus 654, the galaxy had brightened by a factor of 100 in visible light. Soon after its discovery, the Swift Observatory captured its glow in X-rays and ultraviolet. A search of archival observations of the region showed the galaxy actually started to brighten toward the end of 2017. At the time, it was thought this rapid brightening was caused by a star passing close to the galaxy's supermassive black hole. Such a close encounter would cause a tidal disruption event, which would rip the star apart as well as disrupt the flow of gas in the black hole's accretion disk. But this new study casts a shadow on that idea. The team looked at observations of the galactic flare across the full spectrum of light from radio to X-ray. One of the things they noticed was that the intensity of X-rays dropped off very quickly. X-rays are often produced by charged particles spiraling within intense magnetic fields, so this suggested a sudden change in the magnetic field near the black hole. At the same time, the intensity of light in visible and ultraviolet increased, which suggested that parts of the black hole's accretion disk were getting hotter. Neither of these effects is what you'd expect with a tidal disruption event. Instead, a magnetic reversal better fits the data. As the team showed, as a black hole accretion disk undergoes a magnetic reversal, the fields weaken at the outer edges of the accretion disk first. As a result, the disk can heat up more efficiently. At the same time, the weaker magnetic field means that fewer X-rays are produced by charged particles. Once the magnetic field completes its reversal, the disk returns to its original state. This is only the first observation of the magnetic reversal of a galactic black hole. We now know they can occur, but we don't know how common these reversals are. It will take more observations to determine just how many times a galaxy's black hole can become a switch hitter. Let us know your thought on this in the comment box.
For daily video updates, subscribe to Only Facts.